Here's a simple reservoir system. We have a set of inputs. These are the nodes here are randomly set and are not updated. And then we have a single reservoir here, reservoir 1. There's random connections, 10%. Every node here and 1 is randomly connected to 10% of the nodes here. And the nodes here are interconnected. And then there's also, in this system, each node inhibits the nodes in its neighborhood. If I click on here, you can see the nodes that light up are the ones that are connected. So you can see we have connections. Red are excitatory connections over here, the blue inhibitory connections in this neighborhood, and then the recursive connections within this reservoir itself that we have. And then here I can just run this. I'm just setting up a sequence of patterns here, random patterns. Whenever these are integrate and fire, leaky integrate and fire neurons, so they just fire and die out here in the input. When a node fires, it's a kind of a filled-in red square, and then the outline is actually a running total of the last 20 time units going past. Over here, the little squares show just the sum of the activations as we go, the building activations here, and then when a node fires, you see the dark. Here, let me just stop this for a sec. You see the dark red box here when a node is firing after its inputs have reached a certain critical stage. It fires once. And then the borders here show a running total again of how things work. I'm actually cycling through two patterns here. One pattern of random inputs and then a different pattern of random inputs. The little columns here actually just show at each point in time how this network state compares to historic network states of past uptight cycles. And like in inputs here, you can tell here's where our current inputs are, very similar to what I have been getting, but different from this other time period, but very similar to, again, a previous time. I cycle back and forth to these random inputs. So you can see we have an error, similar inputs, an area, different inputs, an area, similar inputs. And the state of this network, this reservoir matches as we go, where we have similar inputs here, these nodes, the running totals of these nodes are on. And we have some different inputs, a different state of the network here, and another set here. Now this currently is not a classic reservoir, because right now I have although the connections within the module, these recursive connections, the inhibitory ones are functioning. In fact, you can see when a node fires, it inhibits, then the running total of the neighboring nodes drops below 0. I'm still working on deciding if we should allow that to drop below 0 or not, but it drops below 0. And turns blue. Blue is negative, red is positive in this sort of scheme. But the excitatory connections within this reservoir are not being active. Over here I have some controls on the inhibitory connections or the recursive excitatory connections, and you can see that's 0. And also the connections between the intermodule connections. If I slow this down, this module will not, the inputs will not, the connections between the inputs here and this network will be less, and these will not become active. They do get a little bit of activity, but again, it leaks away faster than it can build up. As I increase this up, it starts building up more and more, but again, we're still not, there we had one neuron firing, but not many of the neurons can fire with this level. If I keep building this up, at some point we'll get a fair number of neurons firing. So, and then again, as this goes up, we'll get more and more neurons, and we get quickly into a chaotic behavior. So I'm going to drop this back down. And again, we can then add some of the actual excitatory connections within this reservoir and see how they work. So this is the basic reservoir system, and we'll be playing with different aspects of this. And again, this is just one setup, one selection of neurons formats that we'll be looking at.